The objective here is to talk about the addition of nucleophiles to the carbonyls that are present in aldehydes or ketones. We're going to start by focusing on these types of reactions occurring under basic conditions. And we'll talk about the mechanism that typically occurs here, the types of reactions that can take place, and things like that. Then what we're going to do is, in the next segment, transition into what happens under acidic conditions. When we look at the structure of an aldehyde or ketone molecule, so we'll go ahead and draw a representative aldehyde here on the board in blue, and a representative ketone group on the board in blue as well. We recognize that the carbonyl carbon is pretty electrophilic. It's pretty electrophilic because of the fact that the oxygen atom there is electron withdrawing. And we can draw a second resonance structure here for each of these molecules to demonstrate how that oxygen atom is electron withdrawing by resonance. It's going to be pulling those electrons away from the carbon atom, since we have a second hybrid structure here that we can show, wherein our oxygen would take on a negative formal charge and the carbon would take on a positive formal charge. So based on this, we can predict that the carbonyl carbon would be quite electrophilic, and of course electrophiles and nucleophiles are very drawn to one another. And in the case of the reaction of adding nucleophiles to the carbonyl group of aldehydes and ketones, what's going to happen is that the nucleophile is going to attack that very electrophilic carbonyl carbon to get our reaction started. So let's take a look at an example problem here of one of the situations where you can run into nucleophiles adding to the carbonyl group of aldehydes and ketones. And that is, when we think about different nucleophiles, one nucleophile that has come up in the past is the Grignard reagent. So that's our situation where we have carbon that is directly bonded to magnesium in a very, very polarized bond. It's a rare situation where the carbon atom takes on a very strong negative polarization. We don't often see carbons that are negatively polarized, but we see that carbon here. And for the intents and purposes of thinking about how this is going to react, we can really think of that carbon as behaving much like a carb anion. So certainly when we think of that carbon as taking the lion's share of the electron density from that carbon-magnesium bond, and the carbon behaving very much like a carb anion, we can envision that that carbon is going to be a very good nucleophile. So what we'll do is we'll take that nucleophilic carbon atom from our Grignard reagent, which we're using methyl magnesium bromide here in this particular example. And we have to be very careful to protect the Grignard reagent from protic solvents such as water, and even to protect it from water in the environment, because it will react really quickly with that. So we do the first step here typically in ether. So if you see ether listed, keep in mind that that's our solvent there. It's just the soup in which the reaction is taking place. And ether is an aprotic solvent, so it's not going to be donating any protons to engage the carb anion in an acid-base reaction. Instead, it's just going to be hanging out there. And then secondly, after that first reaction has totally taken place, then what we do is we add acid to the solution to neutralize any unreacted Grignard reagent, and also to go about protonating our final product, which we'll see here in just a moment. So let's take a look at the mechanism for this reaction. Again, we're keeping in mind here that we said our Grignard reagent is very strongly nucleophilic. We can think of that carbon as really possessing a lone pair of electrons, since the bond between carbon and magnesium is so strongly polarized. And so that carbon is going to be very, very drawn to the highly electrophilic carbonyl carbon. So it's going to come over and attack that carbonyl carbon. And this is made possible because we can do that without going over the octet rule in that carbon by moving the pi electrons from the carbon-oxygen bond up onto the oxygen. So it's going to take our sp2 trigonal planar carbonyl carbon, and it's going to convert that to an sp3 tetrahedral carbon. So we'll go ahead and draw the intermediate that would result from this. One of the key things and key benefits of this is that our newly installed carbon there is going to result in the formation of a new carbon-carbon bond, which is typically really useful if we're thinking about ways to build molecular complexity. So we have our new methyl group now installed there. And then at this point, the reaction would just chill out until we go onward to step 2 here, where we add that acid. So when we acidify the solution, what's going to happen is that, of course, since we have our oxygen anion there, the oxygen anion is a very good base. That's going to be very eager to grab that proton to finish off this nucleophilic addition reaction, where the nucleophile that was adding here was our methyl group, or methide. So that's going to give us an alcohol as our final product. And one of the main benefits of this is that we can use this method to stitch together new carbon chains onto the existing molecule. So now we've created our alcohol product here through this nucleophilic addition, because we're adding that nucleophilic carbon to the aldehyde or ketone group. We're going to see a bunch of different situations where we can team up a relatively basic nucleophile, such as a Grignard reagent, with a carbonyl group of an aldehyde or ketone. And in each case, we're going to get this same theme taking place, where the nucleophile come in and attack the carbonyl carbon. And then secondly, a protonation step happens to convert the oxygen atom there into a hydroxy group. So let's take a look at a reaction sequence here. It's going to be another example problem of adding Grignards or organometallic compounds to carbonyl groups. So we're going to start here even before we have synthesized the Grignard reagent. So this is going to be a bit of a throwback to earlier topics here. So in the first part of the reaction, we're going to take phenyl bromide. So that's what our pH stands for, is our aromatic ring here. That's directly bonded to bromine. And you should know how to synthesize that based on our discussion of electrophilic aromatic substitution reactions. So we take that and react it with magnesium. The tetrahydrofuran, or THF, is just our aprotic solvent there, because we need to protect our molecule here from protic solvents and protic things in the environment, such as water. So this would give us phenyl magnesium bromide as a result of reacting our magnesium with our phenyl bromide. And then from there, what we'll do is we'll go ahead and bring in, as the second step of our reaction, our aldehyde or ketone molecule. So I'm just going to go ahead here, and since in the last example we did a ketone, we'll do an aldehyde here. We'll do a 3-carbon aldehyde. And much like what we saw in the previous example, our Grignard reagent, it's going to behave much like a carb anion there, that carbon that's bonded to magnesium. So we can show that as such in writing out the mechanism for this, that nucleophilic carbon. And that's one of the carbons of the aromatic ring there, you'll notice, is going to attack the carbonyl carbon of the aldehyde and create our tetrahedral carbon now. So we'll go ahead and draw that in, and now we've got a new bond between the carbon of the aromatic ring and carbon number 1 of our aldehyde. Have our oxygen anion that we fill in there. And our aromatic ring, which I'm just going to abbreviate as pH there for our phenyl group. And that's phenyl with a YL, not an OL. There's no hydroxy group there, so we can't call it phenol with an OL. Then last but not least, to finish off this reaction, we're going to acidify the solution. And that's going to instigate an acid-base reaction between the hydroxy anion and our proton. So we're going to protonate the oxygen anion to lead us to our final product here. Go ahead and plug in that hydrogen to give us our final product. And one thing that always throws people off a little bit with Grignard reagents that I want to highlight here is that people often think that the Grignard reagent has to have an sp3 carbon that is directly bonded to the magnesium. That's not the case. As illustrated here, with our aromatic carbon being directly bonded to the magnesium, that is actually an sp2 carbon. So these Grignard reactions are really, really versatile in terms of the types of carbon atoms that can be accommodated here. You can certainly use an sp2, sp3, really a lot of different options there for your carbon type. And so that's one of the reasons why the Grignard reaction and Grignard reagents are very, very versatile for organic synthesis, where our goal is to build molecular complexity by creating carbon-carbon bonds. As you get into deeper aspects of synthesizing new molecules, one of the key reactions that you'll want to keep kind of hanging out in your back pocket is definitely the Grignard reaction, because that's going to be one of our critical ways that we go about making new carbon-carbon bonds to build complexity. Let's take a look at another permutation of this type of reaction of adding a nucleophile to a carbonyl group, and that is using a deprotonated alkyne as our nucleophile. So if we think back to earlier chapters on alkynes, we learned that you can treat an alkyne with a pretty strong base to deprotonate that alkyne group. So we're going to start with an alkyne molecule. And this has to be a terminal alkyne, of course, because otherwise there would not be an available carbon-hydrogen bond to deprotonate. So I'll show that carbon-hydrogen bond there explicitly on the sp carbon of our alkyne. And it's relevant that carbon is an sp carbon because sp carbons are the most acidic of the different hydrocarbons. So our alkyne group here is going to be much more acidic than any of these alkane carbons, any of the alkane carbon-hydrogen bonds elsewhere in the molecule. So if we treat this with a really strong base, so a strong base is typically going to be something stronger than a base having a oxygen anion. It's typically going to be something that has, for example, a nitrogen anion, because nitrogen is certainly less stable as an anion than as oxygen, since nitrogen is less electronegative. It's less happy, less stable. And so one example of a suitable base for this would be sodium amide, where that nitrogen atom is definitely very supercharged as a base, because that nitrogen is going to have a negative formal charge, and it's pretty unhappy with a negative formal charge. So it's going to be a quite unstable molecule, hence making it a strong base. Other examples of bases that would work here would be something like lithium diisopropyl amide, which is going to have a lithium cation, as you might have guessed from the name, lithium diisopropyl amide. It's going to have a nitrogen and then a diisopropyl group bonded to our nitrogen here. So much like in the case of the sodium amide up above, we're going to have a negatively charged nitrogen atom showing up there. And so that's negatively charged nitrogen atom is what's going to be doing the work in this reaction of acting as a base. Another example here would be molecules that contain hydrides. So for example, sodium hydride NaH. It's going to have a sodium cation, and then the hydrogen is actually a hydride, meaning it has a lone pair of electrons, like so. And so that's going to make that a very strong base as well, because hydrogen really is not happy carrying around a lone pair of electrons. So it's going to make it a very reactive base. So we take one of these bases, whichever one you want off the list, and there are certainly others there as well. We need a very strong base. And we'll take that, react it with our terminal alkyne. And what's going to happen there is that it grabs that proton off the end, off that sp carbon, and it's going to give us a carbanion product as a result of this reaction. So we'll go ahead and draw out our resulting carbanion product. Trying to keep my number of carbon atoms in the chain the same as it was to start with. So this is going to set us up with a carbon nucleophile as well. And from here, the reaction is going to be completely analogous to the reaction that we were observing for our Grignard reagents. So go ahead and bring in our aldehyde or ketone of choice. We'll use benzaldehyde in this case. And so we'll bring our lone pair electrons over from our nucleophile. Those are going to attack the electrophilic carbonyl carbon, forcing the electrons from that pi bond up onto the oxygen. We've seen this drill before. And that's going to give us our intermediate, where we've created now a new carbon-carbon bond, and I'll show that new carbon-carbon bond in green in the structure that I'm about to draw here. We'll also end up with our oxygen anion. And again, our new carbon-carbon bond in green, so I've gone ahead and filled that in. And then I'll go ahead and fill in the rest of that alkyne molecule in red here. Go ahead and fill that in, make sure we haven't created or destroyed any carbon atoms along the way. So it's always a good idea to count your number of carbon atoms from beginning to end of this to make sure you haven't done anything silly along the way. It's awfully easy to leave one out or create an extra one. Looking good so far. Then what we'll do is acidify the solution as our last step of this reaction, much like we were acidifying the solution after the Grignard reagent reacted with the aldehyde or ketone. So once we acidify the solution, that's going to play the role of enabling the very basic oxygen anion to attack that proton and lead us to our final product here. So this use of deprotonated alkynes is a second option that you have for creating new carbon-carbon bonds within these molecules through our nucleophilic addition reactions. You can think of this type of method as being very similar to the Grignard reaction with the aldehyde or ketone in terms of what the reagents are doing here and what we're accomplishing in making a new carbon-carbon bond by having a nucleophilic carbon attack the electrophilic aldehyde or ketone molecule. So these are not the only bases that are available to act in adding across a carbon-carbon carbon-oxygen bond. Another option that we have on the table is to use a cyanide anion. So we'll go ahead and set this up here. So we'll take as our starting material 2-butanone. We've gone in and drawn 2-butanone. We're going to react with hydrogen cyanide, HCN, and we're going to specify here that the pH of the reaction is 10. And so when you see that, that's a clue that we're working under basic conditions here. And so the mechanism that's at play here is going to be very analogous to what we saw for our previous examples. What we'll do here is keeping in mind that our carbon atom is going to act like a carb anion. What we will do is have that carbon acting as an anion come over, attack the carbonyl group, forcing the pi electrons up onto the oxygen, and then that's going to create our tetrahedral carbon now. We'll have an oxygen anion here. And then we've created a new carbon-carbon bond to the nitrile carbon, or the cyanocarbon as you might call it, like so. And then finally, we can protonate that oxygen atom, and you do see some protons available here in the reaction mixture. So we can use a proton to form a covalent bond to our oxygen. So oxygen's acting as our base there to grab the proton, and that's going to finish off this reaction to give us the final major product that we see here. And we would refer to this type of molecule where we have a hydroxy group and a so-called cyano group, or a nitrile group, as you might also call it, on the same carbon. We can refer to that as being a geminal cyanohydrin. So geminal is referring to two groups that are bonded to the same carbon atom. Cyano is referring to our carbon-nitrogen triple bond, and hydrin referring to the fact that we have our hydroxy group there. So this is analogous to a term you might have heard before, which is halohydrin, which was a molecule that had a halogen and a hydroxy group present in it. You could think of this as being analogous to the halohydrin, except now we have a cyano group instead of a halogen group. And since the two groups are on the same carbon, we refer to it as a geminal molecule rather than the halohydrins we were typically talking about as being vicinal halohydrins. Here, this is geminal because they're on the same carbon rather than the two groups being on adjacent carbon atoms. So giving another example of a situation where we can have a basic nucleophile coming in and attacking a carbonyl group. We can go ahead and, thinking of bases, probably one that comes immediately to your mind as a very common base is sodium hydroxide. So if we have a mixture of sodium hydroxide and water, certainly the sodium hydroxide is the stronger nucleophile there, because the sodium hydroxide is definitely the stronger base. It's the more reactive of the two components of the mixture there. So our sodium hydroxide, of course, is a sodium cation, oxygen anion. And so what's going to happen there, following the drill that we saw for these previous examples, is that the hydroxy group, hydroxide anion comes over, attacks the carbonyl, that's the electrophile, and it's going to go through that addition reaction, very, very similar to what we've seen for the other example problems so far. So that'll give us an oxygen anion there, once we've taken the carbonyl pi electrons and move them up onto the oxygen. So to finish this off, what we're going to have to do is protonate. And we have water there available as a proton source in our reaction mixture. So we can use the oxygen anion to grab that proton from water and finish this off with a type of molecule that will be known as a hydrate. The product of adding hydroxide onto the carbonyl group. So we'd refer to this type of structure as a hydrate. And we could perhaps refer to it as a geminal hydrate to emphasize there that our two hydroxy groups are bonded to the exact same carbon atom. We can do a similar reaction using, rather than sodium hydroxide, using methoxide or ethoxide or whatever other source of alkoxide we want to use. So we'll go ahead and do a similar reaction there. Or we'll use sodium methoxide mixed with methanol. The hydrogen there from methanol is going to be our proton source in this reaction. That's why we have it in there. And it is important in these reactions, if you're trying to get a very specific product, you have the structure of the oxygen and alkyl group there that's part of the anion, the same as the OR group that is part of your alcohol, because there is going to be some exchange taking place there through protonation and deprotonation reactions going on amongst the sodium methoxide and the methanol. And so you want to make sure that you're ending up with a consistent O-alkyl group there to act as the nucleophile. And in order for that to be the case, you need to have these two groups matched up there. They need to be the same. So we've got that set up here, and we'll go ahead and create our aldehyde or ketone starting material, whatever we want to use here. And so what we will do here is, following our drill that we've seen in the last several examples, we're just going to take our methoxide anion and have it come over and attack the carbonyl carbon. That forces the electrons from the pi bond up onto the oxygen. And we'll go ahead from there. So we'll end up with our oxygen anion, and we'll create a new carbon-oxygen bond from our methoxy anion, like so. And there would be a hydrogen bonded right here as well. You don't necessarily have to show that, because an align angle formula is implied that it has to be there. So from there, what we'll do then is our last step here of protonating that oxygen anion, and that can occur by reacting with the methanol that's floating around there in the reaction mixture, which is really happy to act as our acid there, so that our base oxygen anion can grab a proton from that to lead us onward to our final product here. So our final product, go ahead and plug in our carbon chain, our methoxy group, our hydroxy group, and that gets us there to the final product. So this particular product, where we have a hydroxy group and an ether group that are geminal to one another, has a very special name that is a common name that you will see floating around a lot, not only here in organic chemistry, but also in biochemistry. And that is referred to as a hemiacetal. So a hemiacetal is a molecule that is one that has a geminal, ether, and hydroxy group, such as what we've seen here. And it definitely has to be that the two groups are geminal to one another. So this molecule right here, particularly this portion that I've circled, would be our hemiacetal group. Hemiacetal groups are really important, particularly in the sugar reactions. So what you will see if you take biochemistry is that most sugars, such as glucose, exist in nature in both open chain form as well as a cyclized form. So they exist both in a linear format and in a cyclic format. And the way they interconvert between the two is through using hemiacetal formation reactions, much like the ones that we've seen here, except that, unlike the reaction that we've seen here so far, the reaction that takes a linear sugar molecule and converts it into a ring is an intramolecular reaction, a reaction where one portion of the molecule reacts with another portion of the molecule to create a ring. And it's super common that intramolecular reactions end up yielding rings. So let's take a look at an example here of an intramolecular hemiacetal formation reaction, much like what you would see in the world of sugars. So a typical sugar will contain both an aldehyde or ketone group, as well as several different hydroxy groups within the molecule. We're going to try to simplify this down just a little bit today, since we're not quite jumping into biochemistry just yet. And we're going to look at a general reaction where we have a hydroxy group at one end of the molecule and an aldehyde or ketone group at the other end of the molecule. We're going to take a look at what would happen in terms of forming a hemiacetal group there through an intramolecular reaction. So this is going to be an intramolecular reaction. Intra meaning all within the same molecule. And we're going to go ahead and create a molecule as an aldehyde group at one end for our example here. This can also take place with a ketone group. And we'll go ahead and draw out a chain here of carbon atoms. We're going to go ahead and do 5 carbon atoms in total in our chain. And then once we have our 5 carbon atoms in place, I'm going to put here a hydroxy group on carbon number 5. So what will happen here, we need to set this reaction up, keeping with our theme at the moment, under basic conditions. So what we're going to do is treat with a base in order to deprotonate our hydroxy group. So our base here is going to deprotonate the hydroxy group. And this intramolecular reaction is going to be most favorable if the product that results from this has a 5 or 6 membered ring. Because if you think way back, we talked about 5 and 6 membered rings being able to adopt particularly stable conformations where the bond angles of the sp3 carbons in the ring very closely approximate the desired 109.5 degree bond angle of an sp3 carbon. And when we think about a 6-membered ring, for example, that particular conformation is referred to as the chair conformation. And you'll very commonly see that the cyclic forms of sugars are written in chair conformations because they are 6-membered rings, and in some cases 5-membered rings, depending upon the exact sugar that we're talking about. Glucose typically is a 6-carbon or 6-atom ring. Ribose is a 5-atom ring, all of which you'll get to if you take biochemistry at some point. But for now, we're just trying to look at overall, in general, what's the reaction that takes place when we have a hydroxy group and an aldehyde or ketone present within the same molecule to get an intramolecular reaction cooking to form a ring. So we'll take our base and we'll use that base to deprotonate our alcohol group. Alcohols have the lowest pK value of what's present here in our reaction mixture, so that's where we're going to remove the proton. Once that's deprotonated, that's going to give us our oxygen anion. That oxygen anion is important because that's going to set us up with anionic basic nucleophile that's present within the same molecule as our aldehyde group. And so we've got two different functional groups in here in the same molecule that are set up very well to react with one another. So our oxygen anion comes over. It's going to form a bond to that carbonyl carbon, forcing the electrons out onto the oxygen from that pi bond. Don't let the fact that we're making a ring here throw you off from the other examples. The mechanism here is exactly the same. The one part that can be a little bit tricky to keep track of is where the atoms are located. Especially if you start to put branches on this chain somewhere, it can get pretty dodgy about where the different branches are located. So my advice to you is to go about numbering the carbon chain in some systematic way here. I've just gone through and numbered 1 through 5, starting with the aldehyde group. So that way I can keep track, even if there is an isopropyl group, carbon 3, and a methyl branch at carbon 4, and all sorts of crazy stuff like that, you can keep track of where those different branches are located by just keeping in mind what's actually reacting here. So let's go ahead then and construct our skeleton that will result from this, and then we'll sort out where the different groups are going to be located on that. So we need to construct a 5-carbon ring, and then there will be a 6th atom there that is your oxygen. So that red arrow, or red arrow right here, that I'm highlighting in yellow, is connecting the oxygen atom to carbon number 1. So that means that we need an oxygen-carbon bond that's going to link that oxygen atom at carbon 5 to carbon number 1. So that's going to give us a 6-membered ring in total, with one of those atoms being an oxygen. So I'm just going to go ahead here, and I'm going to fill in a 6-atom ring where 5 of the atoms are carbon, one of the atoms is oxygen. And I'm going to go ahead and fill in that new carbon-oxygen bond here in red. That was the bond that we were creating with the electron pushing arrow that I'm highlighting right now in red. And so that means that if that new carbon-oxygen bond was coming in, that's going to connect the oxygen to carbon number 1. So therefore in the ring I've put carbon number 1 right there in the upper right corner, going around the ring to 2, 3, 4, and 5. That takes us through that whole carbon chain that we had initially and is now converted into a ring. And this makes sense because carbon number 5 of our chain was connected to the oxygen, carbon number 5 of our ring is connected to the oxygen. So we're all good to go here. Except that we need to figure out, we had some groups on carbon 1 there that we need to account for. And at carbon 1 we had the hydrogen, which we don't necessarily have to show. And we also had that oxygen atom that's going to be coming off of the ring there as a branch. So we need to go ahead and fill that in as our oxygen anion. And then last but not least, our final step here is going to be our protonation. So we just have to go ahead and protonate, and our proton source here could be our conjugate acid that resulted from our base becoming protonated, because we saw in an earlier step there that at the very first step we taken whatever base we were using and grabbed a proton with it. So now that proton that we grabbed by the base at the first step, we can use that to transfer onto the oxygen atom here. Or if we're doing this under conditions that have water present, water can act as the acid here to protonate your oxygen anion. So there's a lot of different options here. It's not the most exciting, most important step of the mechanism. And if we're thinking in terms of biological chemistry, certainly we would expect there is water present, and that's what's happening when we talk about sugar synthesis reactions, is it's going to be the water from the environment that is enabling this protonation step to take place. We'll go ahead and protonate the oxygen atom there, however you like to do that. And that's going to lead us to our final product here. And this is going to be an example of a cyclic hemiacetal molecule. So even though this is in a ring, you should still be able to pick out that what we're dealing with here is a molecule where we have a hydroxy group, and on that same carbon we can pick out that there is an ether group there. So this is still going to be referred to as a hemiacetal molecule, as the type of group that's present here, even though we're now part of a ring rather than just within a chain. So this is still called a hemiacetal. In the next unit, we're going to talk about reactions that are occurring under acidic conditions. And under acidic conditions, we can actually take this step a bit further to end up with a molecule that is a geminal diether, which is referred to as an acetal molecule. So we think of the hemiacetal hemi as being basically halfway to an acetyl molecule. So a full acetyl molecule has two ether groups that are jumping to one another. A hemiacetal still has one hydroxy group and one ether group. So we'll get into that next time when we talk about these types of nucleophilic addition reactions that are occurring under acidic conditions rather than under basic conditions.